Hi there. I'm Mark Cussy, the instructor at the National Test Pilot School. Here we teach pilots and engineers how to evaluate aircraft. You know, see if they perform the way they're designed, and more importantly, make sure they're safe.
Testing airplanes requires that we know a lot more than just how to fly the airplanes. We have to know why an airplane flies the way it does. And that all comes down to physics. Specifically, Newton's laws of physics.
Why is physics so important? Let me put it to you this way.
Without a good understanding of physics, the Wright brothers could never have gotten their flyer off the ground, because they wouldn't have known that the lift of an airplane must overcome its weight for it to fly, and that the thrust of the aircraft must be greater than its drag. But the Wright brothers did understand physics, and they knew about the laws of action and reaction, one of Newton's laws. A lot of early airplane designers didn't bother to study Newton's laws, so they built contraptions that didn't look much like today's airplanes, and for that matter, couldn't fly either.
Newton's laws of physics are still used today by aircraft designers for designing virtually every kind of aircraft, from a small prop job to a supersonic fighter. Using Newton's laws, engineers and pilots figure out things like where to put the wing, how big of an engine does the airplane need, how long of a runway will it take to get this thing off the ground, and when it lands, how good do the brakes have to be to stop it? These are all common questions when it comes to designing an airplane.
By the end of this course, you'll be able to figure out what makes a good airplane and why some designs never make it past the drawing board. You'll know how to calculate the distance of a takeoff and what it takes to get an airplane cruising through the sky as efficiently as possible.
It doesn't hurt to be comfortable either, but we do have to talk about the basics. So real quick, let's review Newton's 3 laws of physics.
Oh, you're back. Good. You know, Newton's first law is often called the Law of Inertia. It talks about bodies at rest and bodies in motion. But we're not talking human bodies. We're talking objects, things, stuff, like my favorite helicopter Igor here. The technical definition goes something like this. A body in motion at a constant speed will remain in motion at that speed unless acted upon by an outside force. A body at rest will remain at rest unless acted upon by an outside force. Piece of cake, right? No? Well, let's look at it this way. Say I take a ride in a spaceship to some faraway galaxy. I'm zipping through space at about 10,000 miles an hour, and there's nothing to slow me down, like the atmosphere or gravity of a nearby planet. When my engine finally runs out of fuel, how long will I stay at that speed? Forever. Back here on Earth, in the car, I'm a body in motion, and I've got inertia. But if I slam on the brakes... Sorry, man, you okay? I'm acted on by this outside force in the form of this seatbelt. Keeps me from going through the windshield.
In a jet, we have seatbelts just like in your car, only a lot more of them. It's because we're moving faster, we have a lot more inertia, requiring a lot more outside force to stop you.
Well, so far we've looked at the seatbelts you use in your car when you're doing 40 miles an hour, and the ones we use in the aircraft when you're doing 200 miles an hour. But what kind of seatbelt would you use when you're traveling at 17,000 miles an hour? That's how fast you have to go to escape Earth's gravitational pull and achieve orbit. In the early days of the space program, scientists had no idea on how to attack that problem. So they built sled tracks like this one here at the Dryden Flight Research Center at Edwards Air Force Base, and the other one at Holloman Air Force Base in New Mexico. There they conducted tests associated with the rapid accelerations and decelerations associated with the space program. They put a man on a rocket sled and shot him at over 400 miles an hour. And then using a water trap, they abruptly stopped the sled. Oh man, that hurts. Nah, just kidding. That was a dummy they fired first. But Colonel Paul Stapps volunteered for the human testing. And while he survived numerous negative G tests, he said that when the sled jerked to a stop, it felt like his eyes had popped right out of their sockets. All of these, the car, the jet, the rocket sled, they demonstrate how the law of inertia works, each one just a bigger example of the other. So let's review the first law again. A body in motion at a constant speed will remain in motion at that speed unless acted upon by an outside force. A body at rest will remain at rest unless acted upon by an outside force. Okay, got it now? On to Newton's second law. Newton's second law states that a force is equal to mass times acceleration, or F equals ma. You know that your weight is just your mass multiplied by the acceleration of gravity. The acceleration of Earth's gravity at the surface of the Earth is 32.2 feet per second squared, and is commonly referred to as g. We can use this in our equation to replace a with the g. Now let's look at the left side of the equation, the F for force. It's not hard to see that your weight is actually a force that demonstrates Newton's second law. So if I step on the scale with all my required flight equipment, we can see that I weigh 155 pounds. Then putting that back into our equation, 155 is equal to m times 32.2. If we divide that out, we can see that my mass is equal to 4.8, and a unit we call slugs. It's a funny name, but the name's not important. Remember that number, because when everything else changes, mass stays the same.
Flying in an aircraft, we often experience more or less than 1G, depending on the maneuver we're performing. That's all going to affect my weight. You've probably experienced something similar in a roller coaster. When you come up over the top, you get real light in the seat, makes you feel like you're going to be thrown out. But then when you go to the bottom, you get pushed down towards the floor of the car, makes you feel like you're really heavy. We experience the same thing in this aircraft, except to a higher degree. If we pull a 2G turn, we're going to feel the same thing as you would in a roller coaster, except now my weight's going to be 309 pounds. And why is that? Okay, let's roll out and talk about it. The reason that is my mass stayed the same at 4.8 slugs. And 1G is still 32.2 feet per second, but my G factor is now 2. So I multiply that all out, it comes out to be 309 pounds. Not bad, eh? Okay, now that we got a pretty good handle on that one, let's do 4Gs. And we're clear left. Okay, so there's 1, 2, 2.5, 3, 3.5, and there's 4. Okay, how much do I weigh? And if you could hurry, that would be good. Okay, we'll roll out. And back to wings level 1G plate. Okay, if you said 618 pounds, you're correct. 618 pounds may sound like a lot. But you got to remember that an air combatant pilot, or a fighter pilot, routinely pulls 6, 7, 8, sometimes even 9 Gs during the course of an aerobatic show or a dogfight. If I pulled 4 Gs, I weighed 618 pounds, but at 9 Gs, I weighed 1,391 pounds. That's a lot of force going towards my feet and legs. And all the blood has a tendency to leave my head and my chest. If too much leaves my head and chest, I can black out. That's why I wear a G-suit. As I pull more G, it inflates, squeezes my legs and my stomach, keeps the blood from going down there, and provides an opposing force to the G's. An opposing force is what Newton's third law is all about. Newton's third law is often thought of as the law of action and reaction. This is a jet engine bay. When the engine's mounted in here, it creates one heck of an action coming right at you. The obvious reaction is it forces the airplane that way. That makes sense. But how does a jet engine work? Just like a balloon that flies away when you let go of it, air comes in here, goes way back into the engine, is heated up, goes faster, comes around the back. It's with a lot of force. That's how a jet works.
With all that force, or action, there has to be an opposite reaction. The reaction makes the airplane move forward, just like the rocket sled you saw earlier. But this time the aircraft has wings which provide lift, forcing it into the air. In fact, there are 4 forces, actions and reactions, working every time an airplane flies. The thrust of the engine is one of the forces making the aircraft move forward. But there's an opposing force to thrust, and it's called drag. Drag is the resistance of the atmosphere on the aircraft, like you feel when you stick your hand out the window of the car while you're driving down the freeway. When the drag equals the thrust, then the aircraft is no longer accelerating, but remains at the same speed since the forces are equal. If thrust is added and becomes greater than the drag, the plane will accelerate. As the plane's speed increases, the drag also increases until the thrust and drag are equal again. There are two other forces as well. Lift is the force provided by the wings as air passes over the airfoil. The opposing force is, of course, weight. It may seem strange, but lift always equals weight, otherwise the aircraft couldn't stay in the air. As you can see, Newton's laws are really quite simple, but a good understanding of them is essential to the development and flight of aircraft.
It's even more important, we're going to test the airplane. I'm teaming up with some of the best test pilots and engineers at the Dryden Flight Research Center, NASA's home of experimental flight tests. And together, we're going to show you the fun side of flight testing Newton's laws. And speaking of fun, we're out of here.